Welcome to this flight test briefing for Albatross UAV aircraft based on a simulated flight dynamic assessment conducted through Unity. The assessment is undertaken by covering several different properties of the aircraft which will be presented through the course of this video. An initial analysis is conducted to check the flight controls and to understand the input and output motions of the UAV. The controls can be left as they are, apart from the rudder and the flaps, which must be reversed. The rudder must be reversed to provide the correct yawing motion, and the flaps reversed to allow for the coefficient of lift to be increased. The other control surfaces can be left as they are. The elevator provides the roll to the left and right motion, as well as the ailerons. The throttle is also checked to ensure the UAV provides the correct motion. A weight and balance test are performed to estimate the ideal center of gravity of the system. This is conducted by the moment arm of the starboard, port and nose gear, and by using the respective loads to calculate the ideal center of gravity. The handling properties can be established by verifying the wheel reaction forces along with the masses. The linear correlation between the calculated results and those generated by the Unity program can be seen in this graph. A thrust test is conducted by using a pressure sensor which is in front of the UAV as shown in the video. It is important to understand how much thrust the system is producing as the RPM of the propeller increases. The graph shows the linear correlation between the thrust and RPM, where a maximum of 28 newtons of thrust is provided through 100 RPM of the blades. To understand the pitching qualities of the UAV, a longitudinal stability test is conducted at varying wind speeds. Through this, the change in response to the elevate input can be analysed, as this motion is dependent on free stream velocity and centre of gravity. This graph shows the wind velocities of 10 meters per second and 27 meters per second, which demonstrates as the free stream velocity increases, the UAV becomes more responsive to elevator inputs, reaching a trimmed flight condition in less time. A test is conducted by varying its longitudinal position of center of gravity to find its optimal position for it to be placed to allow for reasonable elevator inputs, producing an acceptable pitch control. When the center of gravity is placed at low values of the percentage of the aerodynamic chord, very small angles of attack are produced for maximum control input. Alternatively, when the value is increased, the angle of attack is responsive to the deflection, allowing the system to be maneuvered as required. However, positioning beyond 27% of the mean aerodynamic chord can lead to the motion being dramatically unstable. A lateral stability test is conducted over a range of speeds. In order to induce rolling motion, the elevators are deflected in both directions. The values obtained from these tests are produced in the following graphs as shown, which show the effect the degree of roll has on both yaw and angle of attack. The comparisons of these two wind speeds show that at faster speeds, it takes less time to subside, which results in a less intense oscillation from the system. A lateral stability test is conducted over a range of speeds. In order to induce rolling motion, the elevators are deflected in both directions. The values obtained from these tests are produced in the following graphs as shown, which show the effect the degree of roll has on both yaw and angle of attack. The comparisons of these two wind speeds show that at faster speeds, it takes less time to subside, which results in a less intense oscillation from the system. By varying the center of gravity vertically, the response in pitch also varies respectively. A position which is too high would lead to a large nose-up pitching moment being induced, whereas a position too low would create a large nose-down pitching moment which could lead to premature stall. The zero lift pitching moment thrust line which is present is at minus 0.03 meters. Furthermore, it is found that there is minimal change to the angle of attack when the thrust which is applied is increased with varying center of gravity displacements. This graph shows the effects of varying the vertical position of center of gravity with respect to the angle of attack and time. To understand the capabilities of this UAV, a range of tests were conducted within a virtual wind tunnel. The curved slope of the values that were obtained are shown, which provide the coefficient of lift against the angle of attack for different flap settings. The more flap input that there was provided, the higher the coefficient of lift, which when compared to manufacturer's maximum value of 1.4 for a flap deflection of 40 degrees, is different to the maximum lift coefficient of 1.2, which is obtained at 10 degrees. The drag polar of the UAV is also investigated. The trade-off between the lift and drag is therefore provided where the best lift coefficient of 1.66 happens with a drag coefficient of 0.45 with the same flap settings as before. Furthermore, the pitching moment with a varying center of gravity can also be seen. The graph shows how the position of center of gravity affects the stability. A more stable configuration can be achieved by moving the center of gravity towards the nose of the UAV, while moving it further back makes it less stable. At 30% of the mean aerodynamic chord, the gradient is nearly zero, which tells us that this is close to the upper aft of the center of gravity limit for stability. This video shows the UAV responding well to control inputs when maneuvering on the ground, which implies that the center of gravity position at 0.05 is acceptable. The UAV should also maintain speeds below 5 meters per second when taxiing, as above this could lead to the UAV drifting. The following video shows the UAV taking off with a center of gravity position at 0.1. The right wing stalls as soon as the UAV becomes airborne, leading to a crash, hence why this configuration is not acceptable. Alternatively, when the center of gravity is at 0.05, the UAV is more stable and is much easier to fly and maneuver. Also, when there are no control inputs, the takeoff speed of the UAV is around 50 meters per second, and at an altitude of 100 meters, trimmed flight is achieved at 21 meters per second for a RPM of 28,000. The lowest speed at which the steady flight can be achieved for this UAV is around 16 meters per second. The phenomenon in which an aircraft pitches up, losing speed as it climbs, then subsequently pitches down and regains speed is called the fugoid mode. This occurs in an oscillatory manner for a noticeable period of time, which is characterized by its natural frequency of motion and the damping ratio. The graph shows the damping ratio is 0.0134 with a natural frequency of 0.4206 radians per second, where the time to subside is around 1 minute. Using these optimal conditions, a final test is performed through the flight simulation of Unity, showing how these factors make the UAV more stable to fly as it maneuvers its way around the test track. Thank you for watching.